Welcome to Lesson 2 of the training package on the integrated AADL analysis. This lesson continues with the Balsa AADL models that we translated in Lesson 1. For this lesson, we assume that you have completed Lesson 1 and have the translated AADL Balsa model in your model workspace on Asate. We also assume that you have downloaded and imported the Balsa software project into your Asate AADL Navigator. In this lesson, you will learn to add data flow specifications, thread implementations, and flow latency properties to the AADL model and to perform latency analysis. Let's start with the data flows. In AADL, there are four types: flow sinks, flow sources, flow paths, and end-to-end flows. A flow source is the origin of a data flow, and a flow sink is the termination of that flow. A flow path defines the path through a component that a data flow follows from input to output. End-to-end flows define the paths that information travels from a flow source to a flow sink. Like other AADL components, flows have a type and an implementation. The AADL model you translated in Lesson 1 provides a flow sink or flow source for every UOP component port depending on the port direction. Your first task is to add flow paths through the transporters and the ATC UOP in order to build the end-to-end flows necessary for latency analysis. In the context of Balsa, this means you will define paths that begin in the EGI and AirConfig UOPs and terminate in the ADSB UOP. We begin by adding thread implementations to the AADL Balsa model that are meaningful for latency analysis. In the generated file balsapcs.aadl, you will find a declaration for the ATC Manager thread group. Notice that the thread declaration generated by the face translator is empty. Now switch over to the Balsa software project and look at the definition of executable thread. Notice that this thread has input and output ports as well as a complete execution time property declaration. We want to use this thread implementation in the ATC Manager thread group. To do so, move the Balsa software.aadl model file into the Balsa project by dragging it into the Model Gen folder. Next, we update the ATC Manager thread group to use this thread implementation. We add the implementation name to the declaration for the thread in the subcomponents list. Since the newly declared implementation resides in an external project, we need to make an appropriate width clause at the top of the file. Now that the thread declaration is no longer empty, we can add connections between the thread and the features of the thread group. We can also add a flows section in the thread group declaration and create flow declarations between the inputs and the output. We now need to create implementations of these flow paths in the thread group implementation called atcmanager.impl that will go through the thread. Note that the flow path implementations must have the same name as the declarations you have just created. Now we can replace the flow sink and flow source declarations, which were generated by the face translator, with flow paths between the two input ports and the output port. Finally, we need to modify the implementation of the ATC Manager process and create implementations of those flow paths that will travel through the ATC Manager thread group. Note that the flow path implementations must have the same name as the declarations you've just created. With these steps, we have updated the thread groups in the ATC Manager process for latency analysis. Now we need to repeat these steps for the thread groups declared for the ADSB process, the AirConfig process, and the EGI process. See the integrated training guide for details on these necessary changes. Next, we must define the flow paths through the transporter components, which are defined in the file balsaintegrationmodel.aadl. Unlike the UOP components, there are no flow declarations for the transporters. You must add a flow section to each of the three transporters that declares a flow path between the input and the output. With all of the component flows declared, we are ready to define the end-to-end flows through the integrated system that are necessary for latency analysis. Unlike the other types of flow declarations, end-to-end flows only have an implementation. Navigate to the Balsa integration model.impl, which is in this same file, and add a flow section. The end-to-end flow is declared from source to sink following the logical flow from one component flow implementation to the next through connections. Create two end-to-end flows, one from EGI through ATC to ADSB, and one from air config through ATC to ADSB. Notice that flow declarations are called using the component name flow name syntax, while connections are called by name only. For another perspective on the changes you've just made, generate a new diagram for the integrated system implementation Balsa integration model.impl. This is the same implementation you created a diagram for in Lesson 1. Name the new diagram Balsa with flows. You will likely have to edit the diagram as you did before to make it more readable. Your finished diagram should resemble the one shown here. If your data flows are defined correctly, then you should see a clear data flow path through your Balsa system. Any sections that are missing in your diagram indicate that something is missing or incorrect in your flow declarations. Returning to Balsa integration model.aadl, model elements can be tagged with properties that support various types of analyses. AADL comes with predefined properties located in the plugins contribution directory, but you can also write your own properties. Let's add properties to support latency analysis. The latency analysis tool is one of the standard SEI tools that takes timing properties in your AADL model and calculates expected latency values for full end-to-end system flows. The threads that you added to your AADL Balsa model earlier in this lesson have an execution time property. Now, update each transporter declared in Balsa integration model.aadl and add a latency property declaration on each flow path as shown here. This property is declaring that there is a latency of 1 to 2 milliseconds associated with communications across the TSS. Next, modify Balsa integration model.impl to add a latency property declaration for each end-to-end flow. This is your latency budget for the Balsa system that will be compared against the latency analysis results. We finally have enough information to perform latency analysis in the AADL Balsa model. AADL analysis performed on instance models, which resolve the attributes of the declarations and implementations into a single component representation and build the full system hierarchy of the components. First, we need to generate an instance model of the Balsa system. Right-click on the Balsa integration model.impl in the outline view and select Instantiate System. Locate your newly generated instance model in the Instances folder. Go to Analyses, Timing, check Flow Latency. The results of the latency analysis will be added to a directory named Reports that will be generated in the Instances directory. Open the CSV report and verify that the minimum actual latency of both flows is 11 milliseconds. Note that the maximum actual latency is 2016 milliseconds due to the 1 second sampling delay that was generated by the translator for each thread group. This report shows both a failure case as well as a success case. Line 21 shows that the actual minimum latency of 11 milliseconds is within the specified budget, so the test was successful. However, line 22 shows an error message that states the actual maximum latency of 2016 milliseconds is above the upper latency bound of 20 milliseconds. This error is coupled with a warning on both the instance model as well as the latency report. This concludes Lesson 2 of the Integrated AADL Analysis Training Package.